What promotes wakefulness? Cortical arousal or wakefulness is regulated by the ascending reticular activating system. This system, ARAS, A-R-A-S, has two major pathways. From the upper pons to the thalamus to the cortex, here these are predominantly cholinergic cell groups, and they are maximally firing during wakefulness and REM sleep for dreaming, and lowest firing during non-REM. Then the lower pons has projections to the lateral hypothalamic area, the basal forebrain, and the cortex. This particular system is monoaminergic, serotonin, noradrenaline, and histamine. But the end target neurons are cholinergic or GABAergic. Here, maximal firing is during wakefulness, slower during non-REM, but it's absent during REM. And this is an important point to keep in mind, that in REM sleep, this monoaminergic group is silenced, or the firing is absent. Next, let's look at the flip-flop model of wakefulness. The monoaminergic cells situated in three key areas directly stimulate wakefulness. So the dorsal raphe nucleus, we have serotonin. Locus coeruleus, we have noradrenaline. And third, we have the tuberomammillary nucleus, which is histamine. So the inhibition of the sleep-promoting neurons results in the monoaminergic neurons and the orexin neurons becoming unopposed in a way, stronger, therefore promoting wakefulness. Orexin neurons further promote the activity of the monoaminergic nuclei. Now, we've talked about the monoaminergic neurons mainly being noradrenaline, serotonin, histamine. We also talked about orexin, but we haven't mentioned dopamine here. Dopamine neurons in the ventrolateral periaqueductal gray, which is VLPAG, they promote wakefulness as well by acting on D1 and D2 receptors, which further inhibit the sleep-promoting neurons. We know that PAG, periaqueductal gray, plays an important part in trauma-related disorders overall. And PAG is divided into VLPAG, ventrolateral, but also dorsolateral PAG is present. The ventrolateral PAG, VLPAG, promotes emotional overmodulation, which acts as a brake on dorsolateral PAG and LPAG, lateral periaqueductal gray. And we know that this particular emotional overmodulation phenotype in PTSD is associated with passive defensive responses, activation of the parasympathetic nervous system. So this is the pathway that sets up the cascade towards depersonalization, derealization, but ultimately dissociation. And the reason why I mentioned that is one can see that this particular part, the VLPAG, is responsible for activation of the parasympathetic part and therefore reducing arousal overall. Now, dopamine also interacts with orexin. The VTA, where dopamine neurons are situated, they receive input from orexin. So orexin directly activates dopamine as well, thus augmenting the wake-promoting effect. Locus coeruleus, which was the noradrenergic area, is a major effector of orexin neurons. So you've got significant orexin activity, which of course we've seen will activate dopamine, will activate some of the other monoaminergic neurons, and therefore result and promotes wakefulness. Now, locus coeruleus noradrenergic neurons express only orexin-1 receptor. Now, this becomes important in clinical practice, whilst the orexin-2 receptor mediates non-REM sleep. I'll say that again. We basically got orexin-1 receptor situated on locus coeruleus, but it's the orexin-2 receptor that mediates non-REM sleep. So if I now connect this to the use of orexin antagonists such as lemborexant or suvorexant, we know they are orexin-1 and orexin-2 antagonists. But you see, when the locus coeruleus noradrenergic activity is significant, lemborexant may not benefit insomnia or nightmares or otherwise, because the key orexin-2 that promotes non-REM sleep is not present on locus coeruleus. In this case, one may actually get better benefits by targeting the excessive noradrenergic activity through alpha-1 antagonists or alpha-2 agonists.